Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to the last topic and last lecture for the NPTEL course on material and energy balances. So in the last lecture we talked about unsteady state material balances. Today we will talk about unsteady state energy balances. So let us go back to the general balance equation for energy balances. So the general balance equation would be given as input minus output equals accumulation. As energy can neither be created nor be destroyed, we would not have the generation and consumption terms. And if we were to consider an infinitesimally small time interval of time t, time delta t between the time points of t and t plus delta t, you would have the term accumulation as delta E sys, which is the total energy of the system, change in total energy of the system during this period of time, which would be the accumulation term. So the total energy of any system, as we had already learnt, has three components. You have the kinetic energy, potential energy and the internal energy. So it has been represented here as delta U sys plus delta E k sys plus delta E p sys. So the next term you have is the input term. So the input streams can have energy. So the input stream energy multiplied with the time for the rate of input of energy times delta t will give you the total energy input. So that would be given as m dot in, which is the mass flow rate of the inlet stream, times h cap in plus u in squared divided by 2 plus g z in. So this would be the enthalpy, the change the kinetic energy and the potential energy of the inlet stream, and multiplying that with the mass gives you the total energy of the inlet stream, times delta t gives you the total energy which is entering into the system during the time period delta t through the streams which are flowing in. You could also have heat that can be supplied to the system. We have considered heat supplied as positive, so we will have this as plus q dot delta t. So your output streams again can have the overall energy of the output streams, which would be m dot out times h cap out plus u out squared divided by 2 plus g z out times delta t. So we have considered work done by the system to be positive, so we will take ws dot times delta t in the output stream. So this gives us all the energies which are possessed by the system that could change over time in terms of accumulation, all the energies which can come into the system in the form of inlet streams and heat supplied, and all the energy which could leave the system in the form of outlet streams and the work which can be done by the system. So now that we have these equations, these terms, we can substitute them into the general energy balance equation we have, and we would end up with this equation, which is delta U sys plus delta E k sys plus delta E p sys equals m dot n times h cap in plus u n squared by 2 plus u z in g z in times delta t plus q dot delta t minus m dot out times h cap out plus u out squared by 2 plus g z out times delta t minus ws dot times delta t. So this is basically your accumulation equals input minus output term. So if you were to divide this equation by delta t and assume delta t tends to 0 and apply the limits, then you would have du sys dt plus dek sys dt plus dep sys dt equals m dot in times h cap in plus u in squared by 2 plus g z in plus q dot minus m dot out times h cap out plus u out squared by 2 plus g z out minus ws dot. So this equation is actually quite complex, and it can get even more complicated if you have more than one input or output streams. you would have to account for the m dot times h cap u square by 2 h cap plus u square by 2 plus gz for all the streams. If there are multiple inlet streams, you might have multiple of these terms. The summation of all these have to be accounted for as the inlet energy, and similarly for the outlet streams you would have to find the summation of these terms for all the outlet streams. So, because of this, the equation can get extremely complex and cannot be solved unless a number of simplifications are made. So, in general there are many simplifications which are commonly done. We will describe what these are. So, first simplification which is done is the system has to have at most one input and one output, each with the same mass or molar flow rate. So, you cannot have multiple inlets and outlets, and they cannot be, even if it is only one inlet and one outlet, the mass or molar flow rates have to be the same, which means the total mass of the system cannot change with respect to time. Kinetic and potential energy changes have to be negligible. So, this is a very reasonable assumption to make. In the earlier lectures we have actually done this exercise where we have calculated change in enthalpy and change in internal energy, change in kinetic energy and potential energy, and compared these values. Usually they are much smaller for most chemical processes compared to the change in enthalpy. So, these terms which are the kinetic and potential energy terms can be ignored. So, if we were to do this, the equation then simplifies to form d uses dt equals m dot h cap in minus h cap out plus q dot minus ws dot. So, this equation seems simple and neat. However, even this equation is quite difficult to solve. So, further simplifications are actually required. So, the further simplifications which are usually done are given here. Temperature and composition of the system contents should not vary with position within the system, that is, the system should be perfectly mixed. So, if you have a system, there should not be any effect on the position, or the spatial distribution should not be a factor when we are talking about temperature or composition. So, this means that the outlet stream temperature and the system temperature would be the same. So, your T out would be equal to T sys, and both of them would be equal to T, which is the general temperature for the outlet and the outlet stream and the system. There cannot be any phase change or chemical reactions taking place. So, if those are there, then the equation becomes more and more tedious. U cap equals and H cap have to be independent of pressure. So, if there are going to be pressure dependency, then the problem would require many other correlations to be brought in, which will make it extremely difficult to solve. The mean heat capacities of the system, Cp and Cv, which is the Cp mixture which we calculated earlier, have to be independent of the composition and temperature, and hence unchanged with time. So, that is important. So, even if there is some change in composition, you have to assume that the Cp and Cv for the system is remaining a constant, and only with that kind of a system you will be able to solve this equation. So, using these simplifications, the equation then becomes U sys equals m times U cap sys. So, the U cap sys, basically the system internal energy would be the internal energy at a reference temperature plus Cv times T minus the reference temperature. So, this specific internal energy times the total mass of the system will give you the total internal energy of the system. Assuming m, U cap, Tr and Cv are constants, you would end up with d U sys dt equals mCv dt by dt. So, your H cap in, which is the enthalpy of the inlet stream, can be given as Cp times T in minus Tr, where Tr is the reference temperature, and your H cap out would be given as Cp times T out minus Tr. So, T out, as we already mentioned, would be equal to the system temperature, which is given as T. So, your H cap out would be given as Cp times T minus Tr. So, for an open system, if we were to substitute these values back into the equation simplifies to form mCv dt by dt equals m dot Cp T in minus T plus q dot minus ws dot. For a closed system, the equation simplifies to form mCv dt by dt equals q dot minus w dot. So, these are simple equations to work with. So, this is what we can actually solve. So, to summarize, for this equation to be used, the conditions, these conditions have to be valid. There has to be negligible change in kinetic and potential energy. No accumulation of mass has to happen inside the system. The accumulation can happen only for energy. U cap and H cap should be independent of pressure. No phase change or chemical reactions can happen. There has to be uniform system temperature. So, simplifying this and putting them into terms which can change with respect to time and terms which cannot change with respect to time, we can say that the factors that can change with time are temperature, which would be the outlet and the system temperature, temperature of the inlet stream, Q dot, which is the heat transfer between the system and the surroundings, and Ws dot or W dot, which would be the work done on or by the system. The factors that need to remain a constant would be m, which is the total mass of the system, m dot, which is the mass flow rate of the inlet and the outlet streams, Cp and Cv, which are the heat capacities. So, these factors have to remain a constant for these equations to be valid. So, we will consider such simplified systems and try to perform a couple of energy balance problems to fully understand how we can apply unsteady state energy balance calculations. So, here is the first example. A well stirred batch reactor wrapped in an electrical heating mantle is charged with a liquid reaction mixture. The reactants must be heated from an initial temperature of 25 degrees Celsius to 250 degrees Celsius before the reaction can take place at a measurable rate. Use the data given below to determine the time required for this heating to take place. Reactants are given as mass of the reactants is 1.5 kilograms, CV for the reactants is also given, mass of the reactor and the CV for the reactor is also given. The rate of heating Q dot is given as 500 watts. You have been asked to assume negligible reaction and no phase change during the heating. Also, the stirrer adds negligible energy to the system. So, making these assumptions, we would be able to use the equations that we derived. So, whatever we had as conditions are met in this problem. So, we can use the equations to try and solve this problem. So, as you can see, it is a batch reactor, which means it is a closed system. For a closed system, we derived an equation as mCv dt by dt equals Q dot minus W dot. So, here we have been told that the stirrer does not provide any work. So, which means W dot goes to 0. So, the equation simplifies to mCv dt by dt equals Q dot. So, we need to use CV. So, we have been given the CV values for the reactor and the reactants. So, we have to account for both these components when we are talking about increase in temperature. So, we will have to calculate CV for the mixture or average CV. So, average CV can be calculated as the mass fraction for the component times the CV for that particular component and get a summation of that. So, that would mean it is 1500 divided by 4500 times 0.9 plus 3000 divided by 4500 times 0.12. So, this would give the CV average CV as 1710 divided by 4500, which equals 0.38 calories per gram degree Celsius. So, this can be converted to joules per gram degree Celsius as 1.58992 joules per gram degree Celsius. Now, we have the CV for the system, the CV average for the system. So, we also have Q dot, which has been given as 500 watts. We have the total mass of the system, which is 4500 grams or 4.5 kilograms, because we have 3 kilograms of reactor and 1.5 kilograms of the mixture in the reactor. So, giving us 4.5 kilograms. So, we have CV, M and Q dot. So, we need to now find the time taken to increase the temperature from 25 degrees Celsius to 250 degrees Celsius. So, this can easily be done by performing a simple integration. So, you would have integral 25 to 250 m CV dt equals Q dot integral dt small t. So now we have the values for m and Cv which are constants not dependent on temperature or time. So which would mean 4500 times 1.58992 times integral dt from 25 to, actually it is 250, sorry, 250 would be equal to q dot, which is 500 times t. So your t would then be equal to 3219.6 seconds or 53.66 minutes. So you can heat the system from 25 degrees Celsius to 250 degrees Celsius within about 54 minutes if we were to provide a heat of 500 watts. So with this we have solved one example problem which was for a closed system or a batch system. So in the next example problem we will look at an open system. Here is an example for a continuous system. So this problem statement says that an electrical heating coil is immersed in a stirred tank. Solvent at 15 degrees Celsius with heat capacity of 2.1 kilojoules per kilogram degree Celsius is fed into the tank at a rate of 15 kilograms per hour. Heated solvent is discharged at the same flow rate. The tank is filled initially with 125 kilograms of cold solvent at 10 degrees Celsius. The rate of heating by the electric coil is 800 watts. Calculate the time required for the temperature of the solvent to reach 60 degrees Celsius. So the problem is very similar to what we did in the previous problem, except that here it is a continuous system. So we need to use the equation we derived for the continuous system instead of using the equation we had for the closed system. So let us jump right into the problem, try to solve this problem. So the equation we had for the open system was mCv dt by dt equals m dot Cp Tn minus T plus q dot. So here q dot is given as 800 watts and this needs to be converted to kilojoules per kilogram because that is the units for the Cp and Cv terms. So we would convert this to kilojoules per hour as 800 times 3600 divided by 1000. This would be kilojoules per hour. So this value of q dot is then 2.88 times 10 power 3 kilojoules per hour. So now the next step is to substitute the values for m dot, Cp and Cv. So we have only been given the value for Cp. So what would be the value for Cv that we can use? So because it is a liquid system, we can assume Cp is approximately equal to Cv and use the same value for both. So substituting the values for the total mass Cv, Cp and mass flow rates and q dot, we will be able to get this equation to be 125 times 2.1. So we are using the same value as Cp for Cv as well because it is a liquid system times dt by dt equals m dot, which is mass flow rate, which is 15 kilograms per hour, times Cp, which is 2.1, times inlet temperature, which is 15 degrees Celsius, minus T, which is the temperature at time t equals at time t, and this plus q dot, which is 2.88 times 10 power 3. So this equation can then be simplified as 262.5 dt by dt equals 31.5 times 15 minus t plus 2.88 times 10 power 3. So from here you can get dt by dt equals 1.8 minus 0.12 t plus 10.97, giving you 12.77 minus 0.12 t. So dt by dt equals 12.17 minus 0.12 t. So now we need to find the time taken for heating the increasing the temperature from 10 degrees Celsius, which is the system temperature, initial temperature is 10 degrees Celsius, all the way to 60 degrees Celsius. So for that you would have to integrate this system as dt by 12.77 minus 0.12 t from 10 degrees Celsius to 60 degrees Celsius, would be equal to integral 0 to time taken t dt. So, this would be minus 1 divided by 0.12 times ln of 12.77 minus 0.12 t, and applying the limits from 10 to 60 degrees Celsius, and this would be equal to t. So, from here you can solve this equation. So, t would become minus 1 by 0.12 times ln of 12.77 minus 0.12 times 60 divided by 12.77 minus 0.12 times 10, and solving this equation we would get t equals 6.09 hours. So, it would take 6.09 hours to heat the given system from 10 degrees Celsius to 60 degrees Celsius. So, with this we have been able to perform two very simple problems where we did unsteady state energy balances. So, with this we actually come to the end of our course. I hope you enjoyed this course. I hope it was informative and you were able to learn systematic practices and procedures for performing material and energy balances. Thank you.